On November 2, 2009, SMOS was launched from the Placet's Cosmodrome on top of a rocket launcher. SMOS is one of ESA's Earth Explorer missions that address key scientific challenges and demonstrate new technology in space. Carrying a novel instrument to return information on soil moisture and ocean salinity, both key components of the Earth's water cycle, SMOS is advancing our knowledge of how water is cycled between the Earth's surface and the atmosphere. Understanding these exchange processes is crucial for understanding climate change, for improving weather prediction, and, for example, helping to optimize water consumption when growing crops.
SMOS measures directly the surface soil moisture. So this is really the kind of rain gauge of the atmosphere. So we collect the rain and we store it. Measuring surface soil moisture gives us a hint on the rainfall, so we can partition the rainfall. But also looking at its evolution, we can link it to different other things. One of them is, of course, dryness or wetness of the soil, so floods or droughts. But also the fact that the impact of other events, such as El Niño, La Niña, and its impact on the rainfall distribution, hence the wetness. So it is used to infer droughts or monitor the droughts, but also, of course, for food security in many regions, to anticipate crop yield, especially in areas which are limited by rainfall.
This research satellite was originally planned to be in orbit for 5 years, but thanks to Europe's technological excellence, it has already doubled its life in orbit, providing time series data for a variety of applications. For instance, SMOS data is used for ESA's climate change initiative, through which data are compiled to understand how climate variables are changing over time. Its data are also combined with data from other satellites, such as Cryosat, to map the thickness of sea ice, a crucial climate variable.
With SMOS, we have the possibility to measure the sea ice thickness. In particular, the thickness of thin ice we can measure with SMOS. We have also the companion, the ESA Earth Explorer Cryosat. This was specifically designed to measure the sea ice thickness, and Cryosat is great to measure the thickness of thick ice from the freeboard. But with SMOS we can accurately measure the thin ice.
SMOS data are also used to map the freezing and thawing of soil. This is important because frozen soil, and in particular permafrost, acts as a carbon sink. When permafrost thaws, carbon is released back into the atmosphere, amplifying the greenhouse effect. By comparing data over several years, SMOS helps us to better understand variables affected by and affecting climate change. Over the years, SMOS has proven to be a versatile satellite, going way beyond its original scientific goals. Today, SMOS data are even used operationally for weather prediction by organisations such as the European Centre for Medium-Range Weather Forecasts.
SMOS is very important for weather prediction because weather is related to forecast of the atmospheric variables, but it's also related to land surface forecast and ocean forecast, river forecast. And for this, for weather prediction, our strategy is to develop an Earth system approach where we have a consistent forecast for the different components of the Earth system. And in this context, variables which are at the interface between land surface and atmosphere, or ocean and atmosphere, are very important to ensure the consistency across the different Earth system components. And SMOS is exactly that. It is providing information at the interface between the different Earth system components.
Over the course of a decade, SMOS has given the scientific community an unprecedented wealth of data. And while it has long surpassed its intended lifespan, SMOS remains hard at work while new missions are being studied and prepared to ensure continuous data sets with even higher resolutions and improved technology.